All right. Well, hello, everyone, and welcome back to the show. It is great to see all of you right now, which I'm doing. I'm looking at you. Don't you see me looking at you? Can you see that I'm looking at you? Sorry, I hadn't pulled up the live thing. Okay, here we are now. All right. We got Nan. Hello, Nan. Welcome. Alrighty. So we are continuing onward with our Phylomaniacs episodes on the evolution of photosynthesis, things related to it. So joining me as always, we have Peter of Gonna Go For It fame, who said I was allowed to introduce him that way.
He is here, but he's hiding.
Okay.
In the
Okay,
corner.
so he's hiding. And then we also have Neslig, who is one of my editors and the one who is leading us through the evolution of photosynthesis. Welcome back.
Hello, good to be back. It's been a while. That was hilarious.
Well, Peter, now that you're in there, you can stop the creationists from chewing on the wires.
I will do that immediately. I'll be right back.
Can you also appear on the top right corner and upside down? It would be hilarious too.
No, but I can. Wait. What would you do?
Oh, it froze for a second.
It froze. Okay. I
Sorry,
can pretend to be a convict. I can also pretend to be an important man facepalming. There is that.
Now Jackson froze.
Now Jack.
On a very good freeze frame.
Yes.
Huh. Weird. Okay. Well, it's back now, I guess.
But just a quick question. The book that you before we went live, you mentioned the book Crimes Against Humanity. Is it by Adam Jones?
It's by Jeffrey Robertson.
Oh, I got the wrong one then.
It's I mean, that might be good too. I don't know, but yeah. So this one, I'm actually reading. So I kind of carousel a couple books. So I'm reading All the Shah's Men, which is about the first time we overthrew Iran. Which, believe it or not, the agent, the CIA agent, who was in Iran choreographing the overthrow, or at least the first part of it, was Kermit Roosevelt, the grandson of Teddy Roosevelt. And I guess I'd have to think about how that relates him to FDR, because I believe FDR was a cousin of Teddy. So I don't know how that what that makes him. But yeah, so that was Kermit Roosevelt, who was largely involved in that. The other one is America, which is right here on my shelf, by Greg Grandin. Read the first chapter of that. Brutal. It's a brutal book. The first chapter is about the conquistadors invading the Caribbean and absolutely wiping everyone out. Like it's not great. It sucks. Very well written though. It's quite good. And then Crimes Against Humanity is about, that's this right here, is about the concept of human rights through the ages. So only the first 50 pages of the book are pre-World War II, and the other 950 or so are post-World War II. So a lot of it is viewed through the lens of the UN, essentially. So yeah.
So with the book that I sent you, you've got 2 books about crimes against humanity.
Oh, and Dr. Josh Bowen sent me, that's funny, sent me his book on biblical slavery, which I have not touched yet. if he wants me to read that before we do our show, it's gonna be a little while before I get to that then. But anyway, what about you, Nestle? What are you reading?
I'm actually not reading anything at the moment.
Oh, okay, that's fair.
Yeah.
That's fair. Sometimes I have periods where I don't really read anything. I used to read a lot more biology stuff, but now I read a lot more history and political stuff, which isn't good for my mental health, I don't think. Yes, Smitty, the conquistadors brought freedom to the Caribbean. They freed the natives of their lives. You know, I got a look from my wife just now. She's off screen. Yeah, no, it's quite a sad book. But so the first chapter is told from the point of view of a Dominican priest by the name of Bartolome de las Casas, and he was very much opposed to what the conquistadors were doing. So, yeah. Yes, poor Dr. Josh became the slavery guy just by being mad at people who are wrong on the internet. That happens a lot in our in like the skeptic community. There's Jordan Kareem, who we joke that he's the Shroud of Turin guy. So basically, every time someone comes up with a new argument for why the Shroud of Turin is definitely not a middle-age forgery or whatever, a middle-age material, he takes a look at it and goes through it and all that, or debates and whatever. There's Erica, who has debunked to death the Y chromosome argument that creationists like to throw. They're like, oh, the human and Y chromosomes are different, or the like 98% genetic similarity between human and chimps. Every time creationists like Jeffrey Tompkins try to lie about that, she stomps them. Dan Cardinal, that is Creation Myths, he was fighting with Casey Luskin, and basically every time Casey Luskin pops up, he's like whack-a-mole, he just bops him again. Yeah, so it's fun. It's I don't have anybody. I don't think. I feel like we were the long story short guys for a little bit there, but we stopped doing that. I consider that that was a waste of time arguing with him. But
Even though it got a lot of views, it
did get a lot of
yeah.
views. Listen, I know for a fact that that if we just did like combating creationism content, we'd get way more views on this channel. Because I've looked at like the videos we did where we debunked I was going to call him Annoying Orange, a bit of Orange, or Long Story Short, or the Ancient Aliens guy who was
or when a rational mind responded to raw matter.
Yep, that one. Yeah, exactly. So those videos always do better, and it's not just my channel. That's true. Go look at Erica's channel. Go look at Professor Dave. The videos that people do that are debunks get way more views. It's not even close compared to their normal like educational videos, which makes sense. People like drama. People like content like that, so it makes sense.
It's hard. It's like I think it's mostly negative. Like I would rather have like just good educational videos be more popular than debunking videos, because it's always like a reaction,
Mm-hmm.
like it shouldn't be that way. Yeah,
I agree. Yeah, you're right. It is a reaction. I mean, what are you gonna do? People like to watch that. It's entertaining. I mean, I think a lot of the educational stuff is entertaining too, but yeah, it's definitely fun to call somebody a moron, and dunk on their argument and leave them disgraced, in the YouTube or whatever. So exactly, just like that one. So yeah, I mean, that's the gift that keeps on giving, right? Because he'll never go away until he dies. Eric Hovind, it's very infrequent that I see him in anything anymore. Because he used to be all over the place I remember back in the day, he was like doing talks and stuff, and people would dunk on those. But I really haven't seen him do
Eric
much of anything.
is live several times a month.
Oh, okay.
I'm still subscribed to him, so I do get the notifications when he does something. And
Okay.
fun fact, Hovind is back on YouTube with 2 channels.
Oh, so it sounds like those need to get taken down.
So I think he's trying to test the waters. So one he's been streaming to 5 months ago, and the other one 2 months ago and last month. So I think he's trying to figure out if he can sneak his way back in. People aren't watching him.
Yeah.
So
Maya Adkisson makes a good point. It would be easier if there weren't so many people who are wrong on the internet. That would be true. Yeah, that would be a lot easier for all. But we'd be out of the job, wouldn't we, Nestle? Where would we be if there weren't people who were wrong on the internet?
Yeah. I would be less on the internet. I probably.
I would too. I definitely took a step back from Twitter when I stopped, because I said at one point, and it's been several months now, but I was like, I'm making an effort. I'm just not going to argue with people on Twitter anymore, and I really just don't argue with them much anymore. I had like one argument with some people on Blue Sky, but otherwise I just really don't argue with people that much anymore. We're still happy to have creationists on. If creationists ever want to come on this channel and chat with us, we are happy.
Jackson, you're missing out. I am currently specifically not talking to a guy who's responding to me who claims that the God of the Bible is an alien and should be blamed for all the UFO sightings. I am not kidding.
That's at least an interesting theology, I guess.
Yeah, well, he might not be as sane as anyone else, I think. But who knows?
Yeah, probably not. But yeah, so anyway. Okay. All right, Nestle. Well, I think I've talked enough. I will hand it over to you. So please take it away.
All right, but first we need to have the slides. There it is. Can you also make it bigger for E? Thank you. All right. So
feeding Nestle to everything today.
But today we'll be discussing what impacts the photosynthesis had on our planet, and it mostly involves the presence of oxygen. Oxygen was really the sledgehammer that changed everything on Earth. All right, next slide. So just a quick recap. Previously, we did the Sun Eaters 4 weeks ago, I believe.
The best meme.
Yeah. I will keep using this meme for.
It's so good. I love it.
Like that meme it will be the next episode when we discuss like the third chapter is harnessing light. That's when we will go over each and every step of the process of photosynthesis, and that's basically the meme on the left right there. Yeah, that will be a very fun episode. But today we will be discussing how oxygen changes everything. Next slide. So specific sub-chapters within this episode is first we will go over how atmospheric O2 levels has changed across geological time. We will also be discussing the great oxidation episodes, or they are more often called events, but I will just say episode because event it sounds like an instantaneous thing, but it's not an instantaneous thing, of course. So we will be discussing what the potential causes of these great oxidation episodes. And finally, we finally discuss how O2 has radically altered the Earth's geology in many, many, many ways. All right, next slide. So just a recap, photosynthesis it uses light energy from the sun to turn carbon dioxide and water into organic carbon and oxygen, or O2. Respiration which is what we do. We eat organisms to obtain the organic carbon, and we breathed in the oxygen, and we used both of these to turn it back into carbon dioxide and water, and from that reaction we get the energy that we use to power our own bodies. All right, next slide. So, and because of that reason, because like our respiration is like a matching counterpart to photosynthesis, because of that reason, photosynthesis by itself does not guarantee an O2 rich atmosphere. Just because you have photosynthesis on Earth, you can still have a very low O2 presence in the atmosphere. So oxygen production is almost, in the real world, it's almost balanced by respiration, which consumes O2. And we also have fire, for example, and it also consumes oxygen from the atmosphere. So there's like a balance between photosynthesis and respiration and combustion. So in order for O2 to accumulate in the atmosphere, you have to inhibit the respiration of organic carbon somehow. Next slide. And again, as always, if there are any questions, you can just put something in the live chat, or Jackson can always interrupt me as I go. So one obvious way is to bury the carbon produced by photosynthesis. Like when photosynthesis has produced organic carbon, like a tree, for example, that tree can be buried in the ground and become a fossil, and that will prevent that carbon from being combusted or from being eaten by other organisms, and then of course that will leave an O2 surplus behind in the atmosphere. Oh, next slide. One other less familiar way to prevent respiration of organic carbon is that the organic carbon can be respired anaerobically. So instead of using oxygen to respire organic carbon, some organisms use like sulfate or elemental sulfur instead of in place of O2. So you can see the formula in the middle right there: organic carbon plus sulfate or sulfur, and then the product will be carbon dioxide. And in this case, instead of sometimes you also produce water, but the main waste product instead of water is hydrogen sulfide when you respire using sulfur or sulfur compounds. And some microorganisms do this. I believe these are called sulfur reducing or microbes, if I believe, yeah. If I'm incorrect, or anybody can correct me. Are you more familiar with that?
Right. Yeah, I believe that's what they're called.
Yeah, sulfur reducing bacteria. Yes.
Yeah, I don't know any other names for them.
Yeah, but anyway, they produce hydrogen sulfide, so it is pretty. It smells like rotten eggs. So if you have ever been to like a swamp or something, then you have smelled these microbes, and they live in oxygen poor areas in the world. And when this hydrogen sulfide reacts with iron, it can form pyrite or fool's gold, more commonly known. And that pyrite can be also locked in the Earth's crust, and basically this will prevent the organic carbon from being respired aerobically. And again, it will leave behind an oxygen surplus in the atmosphere. Next slide. So, in the long term, this oxygen surplus is balanced by other processes like oxidative weathering, metamorphism, and volcanism. Basically, the rock itself can react with the oxygen in the atmosphere, which prevents oxygen accumulation to accumulate indefinitely. Of course, we cannot have 100% atmosphere, otherwise things will be very bad. But it's kept low because of all these other factors that can consume oxygen from the atmosphere. So we have like a very dynamic feedback between these factors that keep O2 level stable. Like one significant feedback mechanism is the phosphate feedback. So PO4 3-, that's phosphate, that becomes that is the rate limiting nutrient in the ocean right now, and that becomes more available when the ocean becomes anoxic. So when it becomes low in oxygen, the phosphate will dissolve more readily in the water, and from that you can have like algae blooms, which will bloom, undergo photosynthesis, and without oxygen, the or the product of photosynthesis, the organic carbon, will be buried very easily, and then that keeps O2 high as a result from this feedback mechanism. When oxygen is too low, you have more phosphate. More phosphate means more photosynthesis, also more carbon burial, which in turn keeps O2 high. But you also have a negative feedback with fire, for example, which prevents O2 from accumulating indefinitely. But still, O2 levels have changed radically throughout geological history, and we will mention a few examples of this. Next slide. So this is a very interesting figure that I found from a recent review paper, which summarizes how oxygen levels have. There's of course a certain range of uncertainty, but this is mostly agreed upon that today, like in the last, like during the Cretaceous, I will just go to the next slide, and because we will look at each segment individually during the following slide. So next slide. Yes. So during the specifically right now we live in the Cenozoic, the age of mammals is often called, and of course the age of the dinosaurs is called the Mesozoic, and the Mesozoic O2 appear to have been significantly larger today. Like it was about, like today we have a 21% O2 content in the atmosphere, but during the Mesozoic it could have been between 25 and 30%. That's the figures that I have seen at least. But this O2 content in the atmosphere probably changed because of the rise of the angiosperms, the flowering plants. So, just a background, the angiosperm terrestrial evolution between 100 million and 50 million years ago, between that time span, angiosperm diversity in terms of floral species percentage increased from 0.5% to over 80%. So basically, before the angiosperm terrestrial evolution, only 0.5% of the species present were angiosperms. But after this revolution, over 80% were angiosperms. There's a significant change, and that really changed the floral, also the ecosystem as well, and the significantly affected the evolution of mammals too, and also other groups as well. However, during the Cretaceous, even during this terrestrial evolution, the gymnosperms, the conifers, the cycads, etc., they were still dominant in terms of biomass. So most large trees that you would see during the Cretaceous were still gymnosperms, even though most species were angiosperms. But the first angiosperm rainforest appeared like about 6 million years after the extinction event that killed most of the dinosaurs. So what is like one paper that I found is the angiosperm enhanced the negative feedback with wildfires that keeps oxygen below 25%. And it's also significant because above 25%, you really cannot have closed canopy rainforest, because above that percentage, fires will readily burn down a rainforest like that. So most forests during the Cretaceous were like open canopy. They were pretty sparse, relatively speaking, especially relative to the rainforest. But right now, because the oxygen percentage is lower than 25%, that permits the existence of these closed canopy stratified rainforests.
That's interesting. I did not know that. That is very interesting.
Yeah. And also rainforests also prevent wildfires by having high transpiration rates. Like these plants in the rainforest, they make their own weather. So basically, most of the rain that falls in the rainforest, I forget the percentage, but I think it's most of the rain, the water that falls down comes from the plants themselves that they give off in the atmosphere. So they make their
That's
own
pretty
rain.
wild.
Yeah. Next slide. And going back even further, before right between the Paleozoic and Mesozoic, we have the Permian-Jurassic mass extinction event. To summarize, we have for about 1 million years, you have this flat basalt eruption, which could cover North America about 400 feet deep in lava. Pretty big eruption, yeah. Although, of course, that amount of lava did not erupt in one day. It was emitted over this long time span, of course. But still, this eruption ignited coal deposits that were present right beneath these volcanoes, the Siberian traps. This increased the atmospheric CO2 content, the amount of carbon that was emitted was about 170,000 gigatons of carbon. And that increased the atmospheric content from 710 parts per million to 5,600 parts per million. So an 8 times increase in atmospheric CO2 content. So of course we also have the methane as well, and both these greenhouse gases probably increase the global mean surface temperatures by 10 degrees Celsius or about 18 degrees Fahrenheit. That's that amount of global warming during this time. Really significant global. Like right now we are about 1.5 or like 1.1 degree global warming. But during the Permian-Triassic extinction, this of course it was very protracted, 1 million year long. But today, our rate, as I said in the bottom left, right there, our rate of warming and accumulation of CO2 in the atmosphere is about 10 to 100 times greater or faster. But still, we probably won't be as bad as this extinction event unless we continue like this for 10,000 years. If we continue like this for 10,000 years, then yes, we will probably be going through a mass extinction event like the Permian-Triassic mass extinction. It's all about how long and how fast you accumulate these greenhouse gases. So yeah. Also, another effect is that in these Siberian traps also contained evaporite deposits, which has salt and hydrogen sulfate, which and when that ignited, it caused the emission of like sulfuric acid and also, basically acid rain, and that can damage the ozone layer as well. And we have evidence of UV damaged pollen fossils from this time as well. So basically, and also heavy metals from the volcanic eruption, everything went wrong during the Permian-Triassic extinction event. Next slide. So the main killing agents during the extinction event were widespread anoxia. So basically, in the ocean specifically, oxygen contents were probably very low during this time. Because when you warm up the ocean, it contains less. It is able to contain less amount of oxygen. And you also have, of course, ocean acidification as well from the increase in CO2 content. The extreme hothouse effect from this global warming probably also to decrease the latitude temperature gradient. So right now the temperature between the equator and the North and South Pole is the difference is pretty large, and that difference drives the ocean to circulate. But when there is an extreme hothouse, the temperature difference between the North Pole or the poles and the equator is less, and that can stop the ocean from circulating as well, which will ventilate the ocean with O2. And also previously mentioned, these conditions probably also favored the sulfur bacteria that I previously mentioned, and these sulfur bacteria produce toxic hydrogen sulfide as well. Also, one thing to mention is that the condition of low oxygen and high hydrogen sulfide content in aquatic environment is called euxinia. The name refers to the Black Sea, the old Greek name for the Black Sea, the Euxine. And the Black Sea is one of the biggest environments where this condition still occurs. Like the Black Sea doesn't really circulate deep very well. Like the top layer, the bottom layer in the Black Sea remains stagnant, and below a certain depth, there's no oxygen, and there's a lot of hydrogen sulfide in the Black Sea. Yeah. Oh, next slide. And that condition probably also was maybe not completely widespread, but probably more common during the Permian Triassic extinction event, where you have low oxygen and a lot of hydrogen sulfide. Not a fun time to hang around. Next slide. So moving on to the Carboniferous. This is when famously the oxygen content in the atmosphere reached absurd levels, like above 30%, maybe even reaching 35%. At that point, even wet plant matter can burn very easily. So all it takes is a lightning bolt and you have a wildfire, pretty much easily. Yeah, and we also have a lot of fossil evidence from this time when indicating that wildfires were pretty extensive as well. And we also have evidence of fire adaptations in plants. Like you see these giant lycopods or lycophytes. They are sometimes called giant club mosses, but they're actually more closely related to the quillworts than the club mosses that you see right there. And you can see that these plants in the bottom left right there, these plants have almost like they have no branches, low. They only have all their branches are high on the top, and that's probably because they want to keep their branches above the ground in case of a wildfire. We see similar adaptation. Yeah, we see similar adaptations in plants that are adapted to fire. Yeah, today.
Okay.
Mm-hmm. Yes. And the reason for this high oxygen atmosphere during this time was probably an extensive rate of organic carbon burial. Like 90% of our coal comes from the Carboniferous. So a lot of trees were fossilized during this time. And there are two main reasons proposed for why this is the case. One, this is during the Carboniferous, we have the first appearance of trees with a large amount of lignin. And the idea is that the fungi that digest lignin were not around during this time. They have not evolved yet. There's one significant explanation that could account for why a lot of trees were fossilized during this time. But there's also a geological coincidence. Like during this time, you have a lot of lowlands across the hot, humid equator, which probably promoted a lot of peat mires. And you have also perhaps seen the peat mire today. Basically, it's a bog where if there's any plant matter that falls down into the mire, it won't decay. There's almost no oxygen present in these oxygen poor soil, so the carbon will just stay there, and over time, when more sediments are deposited, it can turn into coal over time. So there's two potential reasons for why this happened during this time. Next slide. Also, one significant thing to mention regarding oxygen is the energy pyramid. So the autotrophs are the primary producers. They produce all the food for the whole ecosystem, basically. And the heterotrophs constitute the primary consumers, secondary consumers, and tertiary consumers, etc., etc. The apex predators, basically on the top of the food chain, they occupy levels most often between 4 and 6. That's where the apex predators are situated. So the number of levels is limited because only 10%, as a general rule. Of course, there are some exceptions to this rule, but as an average, only 10% of the energy contained in one level of this energy pyramid is available to the next level. So only 10% of the plants can be, or only 10% of the energy contained in plants can be used by herbivores, for example. And only 10% of the energy contained in the herbivores can be used by the next level in the food chain. So oxygen is the most efficient way to convert organic carbon into energy. And without oxygen, this 10% would be much lower. It would be less efficient to obtain the energy from each trophic level. So this energy pyramid, without oxygen, this energy pyramid would be much smaller with less levels, maybe only 2 levels at the most. So complex ecosystems with long food chains are not possible without plentiful oxygen. Next slide. So this is a significant regarding the Cambrian and also the Silurian and Devonian. Like in the Cambrian, we have also the appearance of complex ecosystems for the first time with the presence of apex predators. Before the Cambrian, we have no apex predators, and one reason for this is the oxygen content in the atmosphere increased to a certain level, which allowed for the appearance of apex predators during this time. Of course, the Cambrian explosion is not only caused by oxygen, it just permits this event from happening. Without oxygen, you wouldn't have a Cambrian explosion. But with oxygen, a Cambrian explosion can happen, but it's not the full explanation, of course.
It lifts the guardrails off.
Yeah, exactly. There is no break anymore. Yeah,
it's kind of like mutations. Like, mutations won't necessarily happen that cause this, but there's the potential for mutations to happen. Yeah.
Mm-hmm. Yeah. There's also probably the reason why, like the timing of the Cambrian explosion. Like before a certain point, the oxygen was just too low, and for any complex ecosystem to occur. But then after a certain point, it could occur. And there are many reasons for why it did, but we won't go into that. We will just focus on the oxygen. The oxygen also had a significant effect during the later periods, like during the Silurian, Devonian. The levels reached, likely due to the appearance of land plants, the oxygen levels went above 15% for the first time in the Earth's history. And that probably contributed to the diversification of active swimmers, or nekton as specifically called, the actively swimming predators like fishes, for example. Like predatory fishes have a pretty high oxygen demand. Below a certain percentage, predatory fish just can't handle this poor oxygen content. And it's also probably one reason for why, like during the Devonian extinction event, probably multiple during the Devonian, there was also probably widespread anoxia. And we also discussed this in one episode of the Ancestors Tale as well, I believe. We went into detail of what caused the Devonian extinction. I believe anoxia was like one of the main culprits.
Yeah, anoxia and changing sea level.
Yes, it's changing sea levels.
And actually, and I sent it in our little chat today, but there was a discussion, and I think it's going to be in a paper, but Science only showed me the discussion about it, or the presentation of it. A paper that's just about to come out on microfossils during like the Cryogenian glaciation event. And I was like, dang, right after we did our video on it, right after, dang. Oh well.
Yeah, it just showed us that science doesn't stop when it will continue. Like,
it's true.
In about like 10 years or 20 years, pretty much every video that you make right now will be maybe a bit outdated. Maybe, maybe not a bit. Yeah, probably. Yeah. All right. Our next slide. So this is basically an overview of how significant events in O2 levels in the atmosphere has changed and affected life on the planet. And of course, life on the planet has in turn affected the O2 content in the atmosphere itself. There's a feedback between the two. But this only concerned the last 540 million years of the Earth's history, and that time frame is the Phanerozoic eon, right? I think it's eon, right? Yeah. Or am I mistaken?
Sorry, yes, you're correct.
Yes,
I
it's
was like,
eon.
where's
Yes.
my? I
Yeah.
forgot I was muted. Yeah, Phanerozoic. Mm-hmm.
Yes, but it's only a small portion of Earth's history. Next slide. So the Phanerozoic is about only 1/5 of Earth's history. You also have the Proterozoic eon before the Phanerozoic, and then before that we have the Archean eon, and before that the Hadean eon. These three eons are often referred to as the Precambrian, but I don't like that. I think it's more accurate to give them individual names. But yeah, but still, next slide.
Well, because it's like 75% of Earth's history is the Precambrian.
Yes, the Precambrian.
And only this 25% is the Phanerozoic, and we just kind of refer to it. I mean, look at that. They're like, you could fit multiple multiple Phanerozoic eons within the Proterozoic and the Archean. Like it's just not even, close.
Yeah, it's not even close. Yeah.
Mm-hmm.
But as you can see here, and also a very good review paper. I think it may not be a review paper. I think it's just an experimental paper as well. I'm not sure. I think there's also a very good recent article that discusses the deep time changes in the atmospheric content of O2, and not only O2 but also CO2 and methane as well. And you can see also here on the left hand scale, that's a logarithmic scale. So each tick above the one below is 10 times greater. So that's one significant thing to bear in mind when you read this figure. All right, and we will discuss segments within this large time frame for how O2 has changed across the eons of Earth's history. Next slide. So regarding the Archean, which lasts from 4 billion to 2.5 billion years ago. So during this time, the carbon dioxide content was about 10 times or even up to 2,500 times greater than today. And you also have a significant larger amount of methane as well in the atmosphere during this time than compared to today. And this is the most likely solution to what's called the faint young sun paradox. Like I will discuss this more in detail later, but just to abbreviate, the sun during its lifetime, it will heat up. So the older it gets, the hotter it gets. But as you go back in time, the sun will be less bright. It will be fainter in the past. And during the Archean, it was about 70-80% as bright as it is today. And the question is, so if the sun was so faint during this time, this would lead to the Earth being frozen over, basically. But of course, during this time, you also have a lot more CO2 and methane in the atmosphere. And these greenhouse gases were probably the reason for why the Archean was not an ice age. It's one of the most likely solutions that we have today. But regarding the oxygen content, the oxygen was pretty much next to non-existent. So the upper limit for oxygen during this time is 0.00002%. So less than a millionth of a percentage. But it's likely closer to a 100 millionth of a percentage. So basically pretty much no oxygen in the atmosphere during this time. And the reason, one reason we know this is because of what's called mass-independent fractionation of sulfur. When sulfur is exposed to a sulfur compounds are exposed to a UV light in the atmosphere, without the presence or without ozone, you have this interaction between sulfur and UV light, which causes this occurrence of mass-independent sulfur fractionation. You also have air-exposed deposits of minerals which contain minerals that are only stable under anoxic conditions. So you have pyrite, you also have siderite and uraninite. These minerals are only stable without oxygen, and yet we find these air-exposed deposits during this time. Next slide. Oh, Peter? There you go. This is a slide that explains what the mass-independent fractionation of sulfur is. So basically, the volcanoes will emit sulfur dioxide and also a bit of hydrogen sulfide, and you have a series of reactions, also interacting with the UV, which causes sulfur to fractionate independently of mass. So and that's what is referred to as mass independent sulfur fractionation. So sulfur mass independent fractionation, or S-MIF, occurs only when these compounds are broken apart by UV light, and they form elemental sulfur, or S8. So when oxygen is present, the products, the S8 that is produced right there on the left, the right end of the figure, the S8 will interact with the oxygen, and the products are thus not preserved. Of course, but during this time, the products were preserved, and that preserves the mass-independent fractionation pattern. Next slide. And this is the pattern that we see. So I apologize now that the time scale has inverted. The 0 is on the left side, and 400 or 4 billion or 4,000 million years is on the right side. So we can see that the green dots are instances of mass-independent fractionation, and that basically ended at the shortly after the end of the Archean period. After this, we have no occurrence of mass-independent fractionation, which indicates the presence of oxygen in the atmosphere. Next slide. So what ended? So what happened? Well, first to mention is that during the Archean, that's probably when we have the evolution of the cyanobacteria. So cyanobacteria are estimated to have appeared around 3.6 to 2.8 billion years ago. So sometime within the Archean. We also have the occurrence of local oxygen oases, so no widespread oxygen in the atmosphere, but some local environments were oxygen rich during this time as well. We also have a few whiffs of oxygen. So again, not widespread, but some whiffs of oxygen during right around the end of the Archean as well. But then around 2.4 to 2.0 billion years ago, that's when we had the Great Oxidation episode, which is indicated by the appearance of oxidized paleosols, like red beds, for example, the rusty iron that has been oxidized by the oxygen, resulting in these red beds deposits. We also have sulfate evaporite deposits, which is also an indicator of oxygen during this time. Then, following this Great Oxidation episode, we also have the so-called boring billion, between 1.85 to 0.85 billion years ago. During this time, the oxygen levels remained more or less stable between 0.05 and 0.2%. So, it's still compared to the Archean, that is a lot of oxygen, but compared to today, we have 21%. So during the boring billion, it was still pretty low by today's standard. But that's changed during what's called the Neoproterozoic oxidation episode, where oxygen levels increased from below 0.2% to between 2 to 10% oxygen levels. So another big jump in oxygen levels. Next slide. So you can probably see a weird pattern with oxygen. So we have like almost, like not exactly of course, but almost a stepwise increase in oxygen. So first you have in Archean almost no oxygen, then during the Great Oxidation episode it jumped up to about 0.1%, and then after the Neoproterozoic oxidation episode it jumped to about between 2 and 10%. So this pattern of long-term stability and short-term fluctuation indicates that oxygen levels are only stable within certain regimes or certain ranges. And these tipping points correspond to the oxidation episodes. So when oxygen, like I found a paper, the citation is on the bottom right there, they indicate that when oxygen is below 0.05%, there is too little oxygen to produce ozone or O3 to exist in the atmosphere. And when there is no O3, the oxygen, whatever oxygen is present, will be destroyed by UV radiation. But above this threshold, you have basically a positive feedback loop between ozone and oxygen. So the more oxygen you have, the more ozone you have, and the more ozone you have, the longer the oxygen can last in the atmosphere. So it's a self-sustaining feedback above this threshold. And then when another threshold is the 2% threshold, when oxidative weathering below 2%, the reaction between the rocks and the oxygen, that keeps it below 2%. But then above this percentage, oxygen begins to overwhelm, the oxygen sinks on Earth. And also this is also the point when the deep oceans start to become oxygenated as well. But what causes these switches? So why do we have these great oxidation episodes? Next slide. So again, just a recap from the previous slides is that the main mechanisms of atmospheric oxygen accumulation, like one main mechanism is the rapid burial of organic carbon, as previously mentioned. The rapid burial of organic carbon also decreases the CO2 content in the atmosphere as well. And it is also coincidentally, these great oxidation episodes has been associated with major glaciations, like the great oxidation episode has been associated with the so-called Huronian glaciation, but it's probably multiple glaciations that occurred during this time as well. And there's also a debate on whether these glaciations were complete snowballs or just slush balls. It's also a debate on that, but they were pretty extensive glaciations during this time, and also during the Neoproterozoic oxidation episode, you also have the glaciations that we mentioned in the last few episodes on the Ancestors Tale. You have the Sturtian, the Maranoan, the Gaskiers as well, and the Baikanuran. These several glaciations that occurred just before the Cambrian period began. Yeah. So the appearance of these glaciations indicate that a rapid burial of carbon could have explained these rises in oxygen, but it may not be the only reason for why. Next slide. So two other mechanisms for oxygen accumulation is you have also a reduced oxygen sink. So as I previously mentioned, rocks formed by volcanic activity often contain chemicals that can react with oxygen in the atmosphere, the oxidative weathering, as I mentioned. So reduced volcanic activity will reduce oxygen sinks, and that also can lead to glaciations as well. So when you have less volcanic activity, less CO2 is also emitted, and it will also lead to glaciations. Again, both these mechanisms can fit both the increase in oxygen and the presence of these glaciations during this time. And one last mechanism, although it's probably not a significant mechanism explaining the oxidation episodes, but you also have the escape of hydrogen. So when ultraviolet radiation breaks apart H2O, forming O2 and hydrogen, the hydrogen is light enough to escape into space, and that will leave the oxygen behind. But this process is not fast enough to push O2 levels to significant levels. Although this I will mention this mechanism later on, because it will be important later on. So keep this in mind. Next slide. Am I still following, or is everybody still following me on this?
Yeah, makes sense to me.
All right. So now we will discuss the specific trigger mechanism or trigger hypotheses that have been proposed to explain these oxidation episodes. So to biotic, the trigger hypothesis involves the evolution of, like I mentioned previously, that cyanobacteria are much older. They evolved much earlier than the great oxidation episode. But some studies indicate that the first multicellular cyanobacteria evolved during the great oxidation episode. It has been proposed that this may explain or may be one factor in explaining the great oxidation episode. Because multicellular cyanobacteria are heavier, they will sink down into the water column faster, so they will be buried more rapidly than single-celled cyanobacteria. That's the idea. And a similar idea goes for the Neoproterozoic oxidation episodes, where you have the before the Neoproterozoic oxidation episodes, you have the cyanobacteria with the dominant plankton in the ocean. But during the Neoproterozoic oxidation episodes, the dominance of eukaryotic algae, they gained dominance over the cyanobacteria. And of course, the eukaryotic algae, the eukaryotes, are much larger. They are even the individual cells are much larger than the cyanobacteria. So they will sink down and be buried more rapidly than that. So that's also one potential explanation for why we have the Neoproterozoic oxidation episode. Next slide. Oh, before I go further, I have to also explain some geology terms. So we have the terms felsic and mafic. Felsic refers to the elemental composition of rock. So felsic rock refers to rock that contains like lighter elements, like rich in silicon, aluminum, potassium, and sodium. The felsic rock has also a low melting temperature and low density compared to mafic rock. Mafic rock is rich in iron, magnesium, and calcium, and that is a high melting temperature relative to the felsic composition. So the Earth's mantle, deep within the Earth, the mantle is ultramafic in composition, but ultramafic is rare on the surface. The youngest ultramafic rock that we have is 2 billion years old. So the upper mantle is not hot enough to produce ultramafic crust anymore. Partial melting of the mantle results in altered composition. So when the mantle melts at ocean spreading centers that will form the mafic basalt, the main type of rock present in the oceanic crust. But then I also have the St. Helens style volcanism on the continents, which will produce like felsic compositional rocks, like granite or granite. That is the main type of rock that we have on the continents. All right, next slide. So one other explanation involved in the Great Oxidation episode is that the upper mantle, like way back during the Archean, the upper mantle was about 200 degrees hotter than today. So what this means is that melting happened at much greater depths, resulting in more ultramafic crust. And this ultramafic crust contains more iron, as previously mentioned. The mafic are richer in iron, and iron reacts with oxygen, consuming it. So during this time, during the Archean, oxygen sinks were more prevalent. But then as the mantle cooled over time, oxygen sinks became less prevalent. So less oxygen consuming. So that is one, the decreasing mantle temperature is one proposed explanation for why we have a great oxidation episode. And also, there's also one to be discussed as well in the ancestor cell, is that during the Neoproterozoic oxidation episode, you have a low prevalence of mid-ocean rich outgassing, which also could explain why we have like these major glaciations during the Cryogenian as well. That's actually the most recent episode, right, that we did? Or was it the second most recent, Jackson?
With the well, see, in the last one we didn't really talk much about oxygenation because it was pretty much entirely about choanoflagellates. It was the sponge's tail.
I mean, we mentioned this paper, the one, like the figure on the bottom left. That paper, we mentioned that I believe in the sponge's tail.
Yeah, that would have been in the sponge's tail. Yeah.
Yes. We mentioned that this low rate of outgassing from these mid-oceanic ridges is one cause behind the Sturtian snowball Earth glaciation. And it is also related to the oxygen. It's also probably one factor that can explain why we have an increase in oxygen as well. Because when you have low volcanic outgassing, it will decrease the prevalence of these oxygen sinks. So the oxygen can just accumulate more readily without this. All right, next slide. So another few reasons is that during the Archean, as I mentioned before, the mantle was much hotter. And what this means is that because when the mantle is hotter, the oceanic crust would have been much thicker than today. Like today, the oceanic crust is about 6 to 7 kilometers thick. But back then, in the Archean, the oceanic crust was about 25 or 35 kilometers thick. So much thicker. We also have something called cross density reversal was shallower, and this because during this time when the crust reversal density was shallower, it made continental crust thinner. So oceanic crust thicker, continental crust thinner. Both these effects would have limited the topographic relief on the planet. And this meant that most continents were submerged mostly. So the only exceptions that you would have was like maybe Iceland style or New Zealand style islands on the planet. Those were the only land masses that were around during this time. So the Archean was a water world. Especially even relative to today. Today is also a water world, of course, because most of the surface is water. But that was even more true way back then. So when the mantle cooled over time, the oceanic crust became thinner, the continental crust became thicker. So there's a more different. So that made the continents rise above the surface of the water. And with the rise of the continents, you also have like more the continents became more felsic in nature. The felsic contains less iron, so less oxygen consuming as well. And this could also explain why we had an oxidation event resulting from the rise of the continents. Next slide. So, like, why would the continents or rise of the continents result in oxygenation episode? Well, today continental shelves are hotspots for organic burial. So, continental shelves are like just off the shore of continents where you have these shallow waters, and these regions only represent about 7 to 10% of the surface area of the oceans, but they represent 15 to 30% of primary production. So it's a the amount of photosynthesis that occurs on these shallow continental shelves is very high. There's a lot more photosynthesis occurring on these shelves than on the deep oceans, for example. And also, you have like 80% of the organic carbon that's being buried is being buried in these regions too. So they are hotspots for organic carbon burial. And so the reason why these shelves result in more burial is because, like for one, sunlight is more readily able to reach further down to the bottom of the ocean right there. These shallow shells will bask in the sun, of course. We also have more nutrients being available from the erosion of the continents on land. So when rain falls on the continents and you have the nutrient runoffs into these continental shelves, there's a lot more nutrients available to the photosynthesizers. And you also have a higher rate of sedimentations. Again, with the nutrient runoffs comes sediments, and the sediments can promote burial of organic carbon more readily as well. And one significant reason is also continental shelves are very geologically stable, so the organic carbon that's being buried remains buried for a very long time. So this is one very significant reason for why we can have a oxidation episode during this time. Next slide. All right, so one last trigger hypothesis that's been proposed is the rotation speed of the Earth. Like today, the Earth rotates once every 24 hours, more or less. But way back then, the Earth spun much faster. So we have shorter days during this time, and we have shorter days. Of course, photosynthesis can not occur during the night. So the idea is that when the Earth slowed down, photosynthesis became more productive over time, and hence more organic carbon was buried when the Earth slowed down. But why does the Earth slow down? Well, we will discuss that more in the next few slides. Next slide. So going way back to 4.5 billion years ago, you have the precursor to Earth, and also a sister planet named Theia. And this is also shortly after the formation of the Earth solar system, you have these two planets coexisting. But at a certain point, next slide, they collided. The collision was at a glanced angle. So what happened was, next slide. What happened was the debris from the impact still continued past the Earth, and the debris from this impact formed two main bodies, as you can see indicated by these two arrows right there. Next slide. So the idea is that like one of these two bodies went again down into the Earth, and that gave a gravitational assist to the smaller body, and that this assist allowed the smaller body to remain in a stable orbit around the Earth. Next slide. And that smaller body became the moon. That's the most recent, like I've seen this proposal by NASA scientists. That's the most recent model regarding the impact that made our moon. All right, next slide. And I really like these artwork by Vitkus Justinas.
Yeah, that's pretty cool.
Yeah, really cool artwork. Yeah, I accidentally found this when I was just searching online for this slideshow. So I put the current size, or the current apparent size of the moon right on the top left right there. So the moon was much closer during this time, during the Hadean as well. Yeah. Oh, next slide. But over time, the moon receded from Earth, so it's still much like during the Archean. It was still much closer to us, of course, than the current distance. But it slowly receded from us. And I also really like this artwork as well. You can also see that this is really cool. I need to mention this. Like way back then, during the Archean, the moon may have been volcanically active still. Like right now, it's volcanically dead. But way back then, the moon may still have volcanoes, and the volcanoes would have produced these volcanic gases, and the moon is not able to hold onto an atmosphere. So one possibility is that the moon may have been a giant comet in the sky during this time, having this comet tail
That is
behind
a
it.
wild thought.
Yeah.
Just like
Yeah.
wasn't there a paper not too long ago that argued that Earth might have had like a ring in like the
Yes.
Ordovician?
Yeah, during the order. Yeah, I've seen it too. Yeah.
Yeah, that's like crazy stuff to think about.
Yeah. I mean, this is a fantastic piece of artwork. Yeah.
It is.
Yeah. But next slide. So why does the Earth slow down in rotation, and why does the Moon recede? Well, there's like a complex gravitational interaction between the Moon and the Earth, and also between the Sun. So first, the Moon gravitational tides, the tides that we experience as the oceanic tides, they are generated by the Moon, but the oceanic tide leads slightly ahead of the Moon, or relative to the Moon, and this because this oceanic tide leads ahead of the Moon, this generates a decelerating torque on the Earth, and this decelerating torque slows down the Earth's rotation. But as a consequence, like again, basic physics, every action has an equal and opposite reaction. This torque also makes the Moon spin faster around the Earth, so it will cause the Moon to go into a higher orbit. So as the Earth slows down, the Moon gains more distance from the Earth over time. But you also have one additional effect from the sun. When the sunlight is absorbed by water vapor and ozone in the upper atmosphere, that heats up the atmosphere, creating thermal tides in the atmosphere. And also, one thing is cooler and denser tidal bulges in the atmosphere lag behind relative to the sun. So what this does is this generates a accelerating torque on the Earth. So the sun is basically accelerating the spin of the planet. Next slide. So one interesting thing about the how oxygen affects it, like I previously mentioned that the ozone absorbing sunlight is one factor that generates this sun the atmospheric thermal tide. So during the boring billion, when you have the presence of oxygen, also the rise of ozone after this event, this enhanced the thermal tide. And when you enhance the thermal tide, this basically is one reason for why the Earth's rotation stabilized during this time. So right now, the accelerating torque of the thermal tide counteracted the decelerating torque of the moon tide that we have. So during this time, the Earth, the rotation of the Earth stayed constant, more or less, during the boring billion. And that's due to oxygen, like partially due to oxygen, the presence of ozone in the atmosphere, that the Earth stopped slowing down during this time. And it's also probably one reason why, like as I mentioned before, like this rotational speed of the Earth can also affect photosynthesis, because the longer days you have, the more photosynthesis you can have and the more burial you can have. So one reason for why during the boring billion your oxygen level stayed constant is because the Earth's rotation stayed constant as well. And it wasn't during the Neoproterozoic oxidation episode when you have these extensive glaciations during the Cryogenian that glaciation decreased the atmospheric water vapor, which weakened the thermal tide. So this allowed the resonance of these tidal forces to be broken, and then once again the Earth's spin start to slow down over time, and possibly allowing oxygen to increase once more in the atmosphere. So pretty wild to think that the oxygen content in the atmosphere both affects the Earth's rotation and is affected by the Earth's rotation as a result as well.
That is pretty interesting.
Yeah. All right, next slide. So as I mentioned, there's like a complex feedbacks between the mechanism, like as I mentioned before, oxygen affects the Earth's rotation, and the Earth's rotation can affect the oxygen content as well. And you have many other reasons that we discussed before: the decreasing oxygen sinks, the cooling of the mantle, and also the rise of the continents as well, and also the onset of plate tectonics, and also the biotic triggers of cyanobacteria and eukaryotic algae. All these things can have could potentially explain why you have these stepwise increases in the atmospheric oxygen content. All right, next slide. So now we have finally finished discussing how oxygen has changed in the atmosphere over time. Now we can go over how oxygen has impacted the geology of the planet. So one interesting thing about the geochemistry is that many elements in the periodic table have a variety of different oxidation states. Like they can have a different number. Each element can lose or gain electrons from other elements, and these are oxidation states. So, and different oxidation states allows different elements to form different compounds and with different properties. So oxygen in particular is a very good oxidant. Well, obviously. Hence why it's named. Well, I believe oxygen was named before the term oxidant was applied to other elements as well. But anyways, oxygen tends to take electrons away from, especially from metals, like copper is one. Copper is one good example. Oxygen takes electrons from copper, forming this copper +1 and copper +2 oxidation state. So when copper has all its electrons, it's copper 0 or elemental copper, and that copper is orange in color. But as oxygen takes away the electrons, the copper becomes oxidized to form copper oxide in the +1+ state, and that copper is red in color. And as the copper becomes even more oxidized, becoming the copper 2+ states, then you can have these blue-green colored minerals forming. And this is also one interesting interesting thing to explain how the Statue of Liberty has changed in color over time. Like originally, the Statue of Liberty would have been the same color as the copper wire in your electronic wiring that you can see in your own house, for example. It would have been the same color originally, but of course, as it's been exposed to the oxygen in the atmosphere, it has changed color over time. All right, next slide. And the same principle applies to the Earth itself, with all its minerals and metals that occur on the planet. So one significant thing is during the Archean, the oceans were ferruginous. They were rich with iron in the 2+ state. Iron in the 2+ state is soluble; it will dissolve in water, and this would have made the oceans appear a deep green in color with the presence of this iron 2+. And this iron in the ocean is also a likely source for the banded iron formations, which form over close to 2/3 of our iron reserves comes from these deposits. So during the Great Oxidation episodes, the oxygen turns this iron 2+ into ferric iron, the iron in the 3+ state. So it becomes it takes another electron, becoming more positively charged. And this iron in the 3+ states, that is insoluble, and it will basically rust out of the oceans. And after the great oxidation episode, the surface oceans were probably rich in oxygen. So the surface oceans became the iron was no longer soluble in the surface ocean, but the deep oceans remained rich in iron. And you also probably have like periodically euxinic conditions where some regions may have been rich in hydrogen sulfide as well. But then, after the second increase in oxidation, the Neoproterozoic oxidation episode, that is when the deep oceans became fully oxygenated. So that ended the banded iron formation. So all of the iron, even in the deep oceans, all of the iron were rusted out from solution. Anoxia still occurs, but these are very local and periodic. Again, I mentioned the Black Sea previously, where you have like one location where anoxia still occurs in the deep water. It tends to be occurring in stratified bodies, with bodies of water that don't circulate the water from the top and the bottom. Yeah. Now, all right, next slide. So did this change in oxygen, like I already mentioned, how it changes the iron composition in the water of the oceans, but it also affects many other elements as well. So as mentioned, iron becomes less soluble in water and it becomes more oxidized, but other metals become more soluble when they become more oxidized, like copper. When copper becomes the +2 state, for example, it will be more soluble in water. Zinc, nickel, magnesium, and molybdenum as well. As you can see in the graph on the left right there, where that some elements increased in prevalence during in the oceans after these oxidation episodes. And this is a very significant implication on the evolution of life. Like many key enzymes rely on copper and zinc. Like one example is zinc finger proteins are among the most abundant proteins in eukaryotic genomes, us included. In animals, they are important transcription factors and hormonal messengers. So these are very big implications. Again, implications of how life has evolved. Next slide. Also, regarding the mineral content of the planet, like this is also one scientist I highly recommend looking up, Robert M. Hazen. I also recommend the book The Story of Earth that he wrote. He's I believe he's a mineralogist or a geologist in general, but he is really big in mineralogy. And this is one of my favorite statements that he has made, is that the great oxidation episode has like doubled or even tripled the number of different minerals that exist on the planet. So Earth is very unique, even not just regarding life, but also regarding its mineral composition. With the presence of oxygen, you can have these elements occurring in different oxidation states. Like one example that I give here is the copper +2+ state, and that can form the mineral azurite and also the mineral malachite. These minerals do not occur without oxygen, because copper cannot exist. Like copper in the 2+ state cannot exist in high amounts without oxygen like that. So with oxygen, you have these minerals, and that made Earth like one sentence that I gave here, one quote on the bottom right that I gave here is that the Earth is the most mineralogically diverse planet in our solar system. All right, next slide. And like we have discussed how oxygen affects the ocean chemistry and also the rock chemistry, but now we can also discuss how oxygen affects the atmospheric chemistry. So during the Archean, without oxygen, it also lacked the ozone, of course, and it was methane rich as well. So one interesting implication is that when methane and carbon dioxide and nitrogen interact with ultraviolet radiation, that can produce an organic haze. Like, well, famously, the organic haze today occurs on the moon Titan, which has a very rich methane atmosphere. And with the reacting with the UV light, that produces these complex organic particles, which is the reason why Titan has this very thick cloud of haze on the upper atmosphere. And the Earth may probably not as extensive as Titan, but the Earth may have had such a haze, a dilute haze compared to Titan, of course. But still, that would have made the atmosphere like a deep orange in color from this haze, like a basically smog, but a much worse than the smog that you are familiar with. Yeah. All right, next slide. So before the great oxidation episodes in the Archean, the Earth would have visually looked very, very differently. The oceans were green from the iron dissolved in it, and the atmosphere may have been a deep orange from the haze that was produced from methane interacting with ultraviolet radiation. All right, next slide. And this is what it would look like without the haze. Again, the continents were mostly submerged below the surface of the water, and the oceans were green from the iron in. All right, next slide. And then after the great oxidation episode, everything changes. The continents were rising above the seas, the oceans turned blue, and the atmosphere turned blue as well. All because of oxygen. Next slide. This was also very a significant implication in the discovery of exoplanets. Like one mechanism that we find distant planets in other solar systems is when the planet orbiting its host star passes in front of the star relative to us, and that you have this dip in brightness of the star, which allows us to detect the presence of a planet orbiting around it. But when the light of the star passes through the atmosphere of this planet, it can also tell us the composition of the atmosphere itself. Next slide. And because oxygen has this significant impact on the atmospheric chemistry, we can probably use this to maybe detect life signatures on distant exoplanets. So when we see a signature like this from an exoplanet indicating the presence of oxygen, I would bet that is an indication of life. Like I'm not convinced that you can have such a rich oxygen atmosphere without the presence of life. All right, next slide. But we are still not done yet. So we have also other things to cover, but we need to cover some backgrounds in these things. We need to discuss a few things about plate tectonics, a few things about the geomagnetic field, and also the carbonate silicate cycle.
Which we did talk about in the
Yes.
Sponge's Tale.
Indeed. All right, next slide. So as I mentioned before, about the topographic relief, but to go in more detail, today Earth is very unique in the topographic occurrence as well. Like the distribution of elevations on Earth is bimodal. There are two common elevations. Like the most common elevation is the continental plains, and also another common elevation is the abyssal plains on the oceans. And you have three rare elevations. You can see that distribution on the top left right there. It basically indicates which elevations are the most common on the surface of the planet, on the Earth. Some elevations occur more common. Of course, the rarest elevation, like the one on top right there, the rarest elevations are the mountain peaks, for example, like Mount Everest. They are not very common. The more commonly you have is the Great Plains on the continent, and also the plains on the ocean as well. And the reason for why we have this bimodal distribution of elevation is because, again, we have these two main compositions in the crust. So we have felsic crust, which compose the continents, and the mafic crust, which compose the oceanic crust. The felsic crust is lighter, less dense compared to the mafic, which is why you have these two different these two bimodal distributions in elevations. Like one, the continental the most common elevation of the continental plane, that is the most common elevation of the felsic crust, and the abyssal plane, the common abyssal plane elevation, is the most common elevation of the oceanic mafic crust. All right, next slide. Oh, I see a question in the live chat. The only question is, what are coppers? Oh, what are copper blocks for?
Yeah, because they're talking about Minecraft over there.
Yeah, I thought it was I thought it was a serious question. All right, all right. I'll continue on. So, but why do we have these two different types of crust? Well, during at the oceanic spreading centers, when in the ocean, like for example, this occurs on the mid-Atlantic oceanic ridge. Like also Iceland is part of this. When the two plates separate from one another, you have what's called a decompression melting occurring in the mantle. So the mantle is pretty hot, but it's still solid. The mantle is solid, and it is kept solid by the high pressure. But when the ocean, when the crust spreads at oceanic spreading centers, the pressure decreases, allowing the mantle to melt and form new crust right there. And this decompression melting will produce mafic crust as a result. And this is why new oceanic crust is mafic in composition. But at the right-hand side, when plates subduct, they bring in water, they introduce water into the mantle. And water is also interesting to mention, is that water acts as it decreases the melting temperature of the mantle, which is pretty weird. Like you would think like, oh, water cools things down. No, water does not cool things down. That is not how water works. Like sometimes water can actually decrease the melting temperature of different rock formations and such. And this will, from this water-induced melting, you have the new crust that it forms is felsic in nature. And this is why the continents are felsic in composition. All right, next slide. And the mantle is solid. It's a like maybe you're familiar. Like I've seen these silly putties for a long time. That's popular a long time.
Yes,
like these,
I mean there's still
yeah.
There's still lots of stuff like that. Yeah.
Yeah. But imagine a silly putty. Now, the silly putty is a solid, but it can like change form. It can flow and such. So the mantle is still able to convect over long periods of time, but it remains in a solid phase nonetheless. Yeah. All right. So, where was I? One other implication of plate tectonics is that the mafic crust and the felsic crust have very different ages as well. The oceanic mafic crust is much younger. Like most of the oceanic crust is less than 200 million years old. There is like one portion in the Mediterranean which may be 340 million years old. But yeah, so most of the ocean crust is relatively young. But the continental crust is different. The continental crust does not subduct, generally speaking. It can remain on the surface forever, unless it is being eroded, of course. But if it's not eroded, the continental crust can remain forever. So most of the continental crust is over 2.5 billion years old. Although the sediments that are on top of the continents are much younger, of course. But when we are talking about the crust itself, the crust deep within deep below the sedimentary rock, that is much older. Yeah. And you can see also an interesting graph on the bottom left, where you can see the different age distributions. Like the Earth's oceanic crust is very young. It's all the way on the bottom right corner of the graph. And then you have the Earth's continental crust, which is much older. But then you have also the Mars, the crust of Mars in the background. That's even older still compared to the Earth's crust, because Mars is tectonically dead. It doesn't really have a tectonic activity much anymore, hence why its crust is very ancient. Next slide. So the Earth is pretty unique in this regard. It has a bimodal distribution of elevations. Like most planets have a unimodal distribution because it has only one type of crust. Like Mars is an exception. It has this weird northern plain, southern highland hemispheric dichotomy. But I won't go into why that is the case. That is a story for a different time. It's still interesting to mention that Mars is also a bimodal. It doesn't have plate tectonics, so it's bimodal for a different reason. All right, next slide. Also, one significant thing to mention is that tectonics basically tectonics is the way a planet loses its internal heat. So, but not all tectonics is plate tectonics. And also during the Earth's history, plate tectonics was probably not the only mode of tectonics that Earth has during its history. So this is still up for debate for exactly why Earth is the only planet that has plate tectonics. Like all the other planets have different tectonic regimes, but it's still a big question of exactly why Earth has plate tectonics. But the three main suspects is sufficient mass. If you are too small, you cannot generate a steep thermal gradient in the mantle, which generates mantle convection. And that is needed for plate tectonics. You also probably need liquid water. Liquid water acts as a lubricant and weakens the crust, which allows the crust to form plates. And it also, as I mentioned previously, it also lowers the melting point of the mantle, which facilitates the subduction of the plates themselves as well. You also need another thing is you need to have the upper mantle needs to be cool enough. If it's too hot, then the crust is too thick and too buoyant to subduct. But when the upper mantle is cool enough, then it can then the crust is able to subduct down into the mantle. All right, next slide. So there's also an interesting review paper that I found on the bottom right there. It discusses the possible different regimes of tectonic activity that has occurred on the Earth. So in order from old to young, first with the proto-Earth stage, where you have a magma ocean, basically. So when the Earth was too hot to even form a crust, we had a magma ocean. That was the tectonic regime during this time. Then as the crust cooled, of the Earth cooled, and then the first crust formed, it was still too hot for plate tectonics. So around this time we had the paper described as a stagnant to sluggish lid, and the main way heat escaped from the interior was via heat pipes. So today we have heat pipes, like Hawaii is one example of a heat pipe. Like we call these hotspots, for example. But during this time, this way of heat transfer from the mantle to space, that is the most prevalent way of heat escape, basically. All right. So the next stage is the primitive Earth stage, where the crust became more solid, it became more mobile, and we have some segments of the crust were perhaps rigid, forming these protoplates, but most of the crust was too hot and too big to form solid plates that we associate with plate tectonics. It's also the time when the continents or the ancient cratons formed. But again, during this time, this was the Archean, most of the continents were still submerged underneath the sea. Next slide. So as we move on to the juvenile Earth, again, the figure goes from bottom to top. So apologies for the reversal of the order for the text. So we go from bottom to top. We have the juvenile Earth. This is the time when the authors of this review paper proposes that the Earth transitioned to the first instance of plate tectonics. The plates were the Earth was cool enough for the plates to form rigid plates separated by narrow zones of deformation, which is the definition of plate tectonics. And also around this time, you also have the continents rose above the ocean. And these two events are associated with the great oxidation episodes and also major glaciations as well. So and we have another potential cause. The transition to plate tectonics may have contributed to the oxidation of Earth as well. Next, following this, we have the youthful Earth phase, where you have early plate tectonics, craton dispersal, and continental assembly. So you have the first continent cycle, where you have like perhaps supercontinents breaking apart and forming again. The middle Earth was like basically the equivalent of the boring billion, according to this paper, where the Earth remained relatively stable. But then another significant transition occurred around 0.8 billion years ago, when the upper mantle cooled enough to permit modern style plate tectonics. So one difference between the early plate tectonics is that the modern plate tectonics now slab pull became the dominant driver of plate movement. Like before, the dominant force that moved the plates was convection. But right now, in modern plate tectonics, the dominant driver of plate movement is the fact that the subducting plate pulls on the plate itself, basically. So slab pull became the dominant driver of plate movement. You also have one interesting, I gave a citation right there as well, which is also interesting to mention that around this time, the inner core of Earth may have solidified for the first time. And this also perhaps strengthened the magnetic field, which we'll be discussing in a later slide. And again, both of these events, the modern plate tectonics and the inner core solidification, are associated with the second oxidation episode and also major glaciation. So we have another potential factors that contribute to this event as well. All right, next slide. So about the magnetic field. So the reason why we have a magnetic field is the same flux of heat escaping from the interior to the exterior. So you have in the Earth's mantle, you have mainly radioactivity and primordial heat from the Earth's formation. You also have 10% of the internal heat comes from latent heat, as the outer core, like the outer core of the planet, is liquid and the inner core is solid. But as the planet cools over time, the outer core solidifies onto the inner core. And when that happens, latent heat is released from this solidification. And that gives about another 10% of the Earth's internal energy budget. The tidal effect of the moon has a very minor effect on the internal heat of the Earth. So, but the geodynamo is driven by the convection of the liquid metal in the outer core, and that convection is driven by the escape of heat from the interior of the planet. This is also a Coriolis effect as well going on, probably, as the Earth, because the Earth spins around, the magnetic fluid circulates more vigorously, which will generate a geodynamo and producing a magnetic field that protects us from dangerous radiation from space. Yeah. All right, next slide. And one last thing to discuss is the carbonate silicate cycle. This again, we discussed this also in one episode on in the ancestor cell, where you have the presence of water and carbon dioxide in the atmosphere. They can react with one another to produce carbonic acid, and this carbonic acid reacts with the calcium silicate in the crust. And this is called silicate weathering. So the reaction between the carbonic acid and the silicate produces calcium and bicarbonate. The calcium and bicarbonate can form calcium. The calcium and the bicarbonate can form calcium carbonate shells, like what's happening in some organisms as well. Like one famous example is the corals, which you also mentioned before, that they construct these calcium carbonate shells from the calcium as well, and this calcium carbonate will sink down to the surface of the oceanic crust. And this whole process takes up carbon dioxide from the atmosphere, which will decrease the carbon dioxide in the atmosphere. And as a result of the reduced greenhouse effect, it will decrease the temperature of the planet. But then the cycle needs to be completed when the calcium carbonate goes down into the mantle and is being brought back up by volcanic activity. The carbon dioxide is released once again from this, and that goes back into the atmosphere. So the whole cycle completes from this. But then, significantly to mention is that the silicate weathering is temperature dependent. If it's cold, then silicate weathering is less occurs at a lower rate. So what this means is that less carbon dioxide is then absorbed from the atmosphere, thereby increasing carbon dioxide. But then as a result, temperatures increases, which will increase the silicate weathering, which will increase carbon removal, and thus this feedback stabilizes the Earth's climate over a very long time periods. Yeah. All right, next slide. All right, so a last thing to go over is, like I've been covering plate tectonics and also the carbonate silicate cycle and also the geodynamo magnetic field as well. But I need to give you one more background to explain why all these things are relevant to oxygen. So when we look at the sun in the visible range of the electromagnetic spectrum, we see the surface of the sun as a pretty much very calm surface, more or less. Like, so it's only 5,800 degrees Kelvin. You can see the image on the left right there. But when we see the sun in the ultraviolet and the X-ray spectrum, we can see that the upper atmosphere, the chromosphere and the corona of the sun is much, much hotter. Like the chromosphere. Oh, hold on. I have a. Oh, never mind. I had a pop-up on my desk for some reason. All right, no worries. The chromosphere is about 20,000 Kelvin, and the corona can be as hot as 1 million or even 8 million degrees Kelvin. So much, much hotter compared to the surface of the sun. So why is this the case? Well, next slide. So when we see the sun in the extreme ultraviolet, we can see that these magnetic storms create these loops of magnetic fields. And that's probably, like, again, it's also one thing that's still discussed between physicists, like astrophysicists especially, exactly to why the corona is much, much hotter. But it is probably to do with this magnetic activity, for the reason why the upper atmosphere is much hotter compared to the surface of the sun. Yeah. Next slide. So another thing to go over is that as I mentioned before, the faint young sun paradox. If we go back into the past, the sun was much fainter compared to today. But why is this the case? Well, as the sun a star like the sun ages over time, it builds up the helium in its core. The helium is the leftover product of fusion, which is the process that powers the sun. But when the helium core grows over time, the hydrogen core shrinks. It's less able to withstand the pressure of gravity, so it shrinks. But because it shrinks, the core will heat up. And when the core heats up, the outer layer will also heat up, which will make it brighter. So as the helium core grows, the sun will become larger and brighter. Eventually, it will turn into a red giant, as you can see on the right hand side right there. And that will be about like 10, I think about 10 billion years from now, when the sun will reach that state. But one other thing to consider is that when the sun increases in size like this, it will also slow down in rotation. Again, you can also remember this from physics 101. If you have a figure skater spreading their arms out, they will slow down in spin, of course. And when they bring their arms back in, they will speed up in rotation. So the conservation of angular momentum explains that. I mean, it also applies here. When the sun becomes larger, it will slow down in rotation. So what this means is that the faint young sun rotated much faster. And because rotation also affects the magnetic activity that I previously mentioned, which will probably this probably means that the faint young sun is much more active in the ultraviolet and the X-ray than today.
Whoa, Nestle, you're roboting.
Oh.
And I will distract everyone with my juggling abilities.
Am I still roboting?
Nope, you sound fine.
All right, I apologize for that. But I'm still. Does everybody still following me on this?
Yeah,
I've been rambling for a very long time, so I hope I'm not losing anybody here.
No,
so
it's fine.
Again, even though the sun was much fainter in the past, it probably emitted a much more ultraviolet radiation and also X-rays because of this fast rotation. And we also see, I believe, when we look out into space and we see young stars, they are also much more active in the ultraviolet and X-ray spectrums as well, because they are rotating much faster because of this. All right, next slide. And this UV activity has a very significant implication on Earth. Like today, as I mentioned before, UV light and also X-ray light will break apart water, H2O. It will break apart H2O into oxygen and hydrogen. And the hydrogen will escape into space, leaving the oxygen behind. And you can see a good image on the left right there, where you will see the Earth in a spectrum that sees hydrogen escaping. So basically, the Earth has a halo of hydrogen that is constantly leaking from the planet. But today, the hydrogen escape is not very high. Only 3 kilograms of hydrogen escapes per second. No, not a lot. So at that rate, all the oceans will be gone in about 1.6 billion years. So we have plenty of time until that happens. But way back in the past, without ozone and with the presence of methane exposed to ultraviolet radiation, this increases the rate by a factor of 1,000. Thus, this will remove the oceans in about 1.6 billion years. And combined with the addition of the UV X-ray active young sun, Earth likely lost about 1 world ocean during its early history. So we used to have double the water, or maybe even more, at the beginning than we have now, because of this hydrogen escape. So another thing to mention is that what if Earth never had ozone or oxygen? If it never had oxygen, then it probably would have lost all the water by now. So the presence of oxygen prevented, and the presence of oxygen and also the presence of the ozone that protects us from this radiation permitted Earth to retain the water it has for a longer time. Next slide.
Well, good thing for that.
Yes. So we see like the three sister planets of our Earth. On the left, you have Venus. Like there's still debate on whether Venus had water. It perhaps did not have water. I'm not sure. But if it did, it probably lost its water due to this process very, very early in its history. So water escaped as hydrogen into the space, and that without water you don't have the carbonate silicate cycle anymore. And that's probably the reason why Venus developed a CO2 rich atmosphere. There was no mechanism that could absorb the CO2 emitted from the volcanoes back into the mantle. So what basically happened without water, CO2 kept building up, and then there's a runaway greenhouse effect on Venus because all the water has been gone. On Mars, there's a different situation. Early on in its history, because of its small size, it had a geodynamo. Like its internal heat was escaping very rapidly during the early phase of its history, and that rapid escape of heat generated a geodynamo. Like there is evidence of a magnetic field during its early time. It's probably allowed it to retain water during, I don't know exactly for how long it was. I think it's like a couple of 100 million years during the early history. So water, like that magnetic field, water was retained, but then eventually the Mars cooled down too much, and then the magnetic field shut down. I put the date on it. It shut down around 4 billion to 3.8 billion years ago. So that's when the magnetic field shut down. And after that point, probably all the water started to become exposed to the ultraviolet radiation, and all the hydrogen escaped, and the oxygen that was left behind rusted the planet red. And that is the reason why Mars is red. So all the water was broken apart into hydrogen and oxygen. The hydrogen escaped into space, and the oxygen was left behind, rusting the surface of Mars. But the Earth is different because we had a bit of photosynthesis, all the imported processes like plate tectonics, the carbonate silicate cycle were still continued on, and that allowed Earth to maintain a livable, a habitable state. But without oxygen, next slide. Next slide. So without oxygen, all the water would have escaped into space by now. So that would shut down plate tectonics, that would shut down the carbonate silicate cycle, that would shut down also the geomagnetic field as well. And we will probably end up in a similar state as Venus if this would have happened. So without photosynthesis, we would be dead. Life would not be existing anymore. So thank goodness for photosynthesis and the oxygen it has left behind for us. It's not only there because we needed to breathe the air. We also needed to have a livable planet as well for all life on the Earth. All right, next slide. So just a summarize of the impact that photosynthesis had, and specifically oxygen had. Like the photosynthesis completely changed the course of evolution on the planet. Like complex multicellular life, especially visible to the naked eye, and long food chain ecosystems would be next to non-existent without oxygen. Also, the carbon cycle is significantly affected as well by photosynthesis. Like the carbon flux of or the yearly carbon flux is about 120 gigatons. So 120 gigatons of carbon overturned every single year by photosynthesis. And we also can see a significant like a significant increase and decrease in carbon dioxide content in the atmosphere during the seasons, like during the summer, because most of the terrestrial surface occurs on the northern hemisphere. That means when the northern hemisphere has a summer, more carbon dioxide is being absorbed from the atmosphere. So we see a noticeable decrease in the carbon dioxide atmosphere during the summer, and during the winter we see the opposite. We see a significant increase in CO2 content in the atmosphere because of photosynthesis. It also affects the energy flow on the planet. Like photosynthesis captures about 140 terabytes of energy from the sun. It's only a fraction of the energy that the sun provides to us, but it's still about 8 to 9 times as much as the total power that we generate from our civilization. And the pigments that are responsible for this energy capture makes the Earth look green. And as also previously mentioned, the atmosphere, the O2-rich atmosphere, has drastically altered the chemistry on the planet. Many new minerals has come into existence, and it has changed the atmospheric and oceanic chemistry. And this change makes the Earth look blue. So the pale blue-green dot that we are familiar with would not exist without the presence of oxygen from photosynthesis. All right, next slide. And that's it. I went a little bit over time, but not much. And for the next
That's
chapter,
okay.
we will discuss the process of photosynthesis itself in more detail.
Yay, the bane of students everywhere.
Yes.
I actually, I didn't like. Oh no, what's going on here?
Oh,
I didn't like photosynthesis when I was when I was a biology student, but then when I became a master's student, and I had to like learn it so I could TA the botany lab, then I was like, oh, this actually makes a lot of sense. Everything's falling into place now. Okay.
Yeah. It's
Very
all
interesting.
coming together.
It's all coming together, yeah.
Yeah.
Well, very interesting. Thank you, Nestling.
Also, one thing to mention is I will be on vacation for the next 5 weeks, so I won't be here available. Yeah,
that's entirely too long. I guess we'll have to.
We have to wait until the next chapter. And I'm still working on the next chapter. I'm not finished.
That's fair. You put a lot of effort into these slides.
Yeah. I want to do this justice. Yeah.
Yeah, absolutely. Okay.
Oh, any questions perhaps in the live chat before we end this?
I didn't see any. I kept taking a look, but I didn't see any. But yeah, I thought it was fun. I liked it. Okay. Well, thank you, Nestling. And thank you, Peter, for hosting as always.
More than happy to.
I expected him to pop in.
No, I'm still.
And thank you.
I'm still in hiding. I'm working on something for the next show, I think.
Oh, okay.
Because I don't think if that we can have it on this show already. Although I'm actually not entirely sure.
Okay. Well,
you know when it was the first time I learned about how oxygen has like allowed Earth to retain its water. Like it was from Nick Lane's book, the how oxygen. What's the exact title again? The oxygen, the molecule that built the world, I believe. Yeah.
Okay.
And that's the book where he goes over, where he mentions the fact that oxygen inhibits the escape of hydrogen into space, allowing Earth to keep its water like that.
Okay.
That made my jaw drop. Like I did not know that it had such an impact on the trajectory of how the planet changed over time.
Yeah, absolutely.
Yeah.
Okay. Well, thank you, Nestling, and thank you, Peter, and thank you everybody in the live chat for watching. And we will see all of you next week. So bye, everybody.
Bye.